Good evening, Professor. This is assignment number 4 for Big Data Analytics. So, in this presentation, I'm going to walk through the technical architecture of Delta Airlines Hadoop-based data lake and explain how each component works together to support real-time analytics, predictive maintenance, and large-scale operational intelligence. Now, why why is Hadoop required over here? So Delta Airlines faced several key challenges before adopting a data lake approach. The reservation, crew, maintenance, and telemetry systems were all siloed, making it impossible to get a unified operational view. Aircraft produces massive volumes of IoT sensor data that traditional systems simply could not handle at any scale. Analytic jobs were slow, real-time monitoring was limited, and predictive maintenance required merging historical and live telemetry data in ways their existing infrastructure couldn't support. These challenges led Delta to adopt a Hadoop-based system. So let us look at the architectural diagram. So let's walk through the entire architectural diagram from left to right. We begin with the airline data sources, which include the aircraft engine and flight control, sensor telemetry, reservation and passenger data, which is also the PNR, crew scheduling systems, maintenance logs, aircraft health databases, airport IoT systems such as gate sensors and baggage systems, external sources like weather, turbulence maps, and FAA traffic leads. All of these systems feed into the ingestion layer, which is technically the first layer, which is the first active zone in the data lake architecture. Kafka handles high volume streaming telemetry from the aircraft. This includes measurements such as engine temperature, vibration levels, and so on and so forth. Aircraft would then send thousands of data points per second, and Kafka keeps up with this load and it streams it reliably into Hadoop. Flume then collects log-heavy data such as aircraft maintenance notes, cockpit logs, and operational logs from the airport systems. Scoop then comes into play, which is used for bulk ingestion from structured operational databases, for example, reservation systems, crew assignment tables, and flight schedules. Since airlines still rely heavily on relational systems, Scoop is essential for synchronizing these operational datasets into Hadoop. Finally, the API ingestion is used for external feeds, which is the real-time weather data, FAA air traffic restrictions, airport delays, and turbulence models. All of these raw data lands into the HDFS raw zone. This zone keeps the data exactly as it arrives without any transformation. It stores different formats like CSV, JSON, Avro, Parquet, IoT logs, binary sensor dumps, and unstructured maintenance notes. The next layer is the compute layer, which is coordinated by Yarn. This is where all the processing engines run. Spark handles the majority of ETL transformation and batch analysis, and Spark MATLAB runs the machine learning pipelines for Delta. This includes models for predicting component failures, estimating injury wear, and forecasting potential delays based on weather and congestion. Then Hive and Test provide a SQL engine for large-scale analytical queries and regulatory reporting. MapReduce is still used in some workflows that still require deterministic batch-style parallel processing. HBase enables millisecond-level lookups. For example, when operational staff wants to check a real-time health aircraft health indicator or whether a component has exceeded its vibration threshold. As data moves from processing to storage, it enters the curated analytics zone of the HDFS. Here, data is stored in optimized formats like Parquet and ORC. This layer contains clean, joined, and well-modeled datasets organized by time, aircraft tail number, route, crew pairing, and maintenance cycles. Finally, the output flows to dashboards, predictive maintenance systems, delay predicting engines, and fuel optimization models, which are used by Delta's operational teams and maintenance engineers. Security and governance then wrap up the entire system, and Apache Ranger manages authorization policies, and Apache Atlas tracks lineage and metadata, which is critically important for FAA and safety compliance. Spark Streaming and Kafka together enable data to process telemetry in real time, and And Hive is heavily used for multi-year analytical workloads such as identifying delay patterns, fuel trends, and so on. Now, in summary, Delta Airlines uses Hadoop to unify telemetry, weather, passenger, and operational data into a single data lake. This architecture supports real-time analytics, predictive maintenance, and machine learning with high-speed operational dashboards. By centralizing and processing data at such a scale, Delta significantly reduces delays, improves reliability, and enhances maintenance and planning. Thank you, Professor.